Hello everyone, I am Dr. Gitumoni Sharma, Associate Professor, Department of Mathematics, USTM. Today I am going to take a class on special theory of relativity. Today's my topic is transformation equation for acceleration, application of Einstein velocity addition theorem and Lorentz consequences. Let me talk first about keywords of my lecture. These are transformation equation for acceleration, Einstein velocity addition theorem's application and Lorentz consequences. We know that there are two frames always considered, one is a traced S frame and other is moving frame S dash frame with a constant velocity v. Let us consider a particle which has coordinate x, y, z, t with respect to S frame and x dash, y dash, z dash, t dash with respect to S dash frame. Here two frame consider S and S dash. S frame is at rest position which has velocity 0 and S dash moving with a constant velocity, and one particle is considered, a black circle is known as is assumed as a particle, and this particle position x, y, z with respect to S frame and its time is t, observed time is t from S frame, and x dash, y dash, z dash with respect to the S dash frame, and observed time with respect to S dash frame is t dash. Let us assume a particle is moving with a velocity v with respect to s and v dash with respect to s dash. So, just I said that we consider a particle which has two coordinate according to s frame and according to s dash frame, and respective time according to s and s dash are t and t dash. So, if the particle start to move according to s and s dash frame, then obviously we get the velocity transformation equation and acceleration transformation equation. Velocity transformation equation last class we have discussed in my previous class. So, if let us assume that the velocity of the particle according to S frame it is capital V and according to S dash frame it is capital V dash, and their corresponding time are t and t dash. So, velocity transformation equation last class we have discussed, V dash is equal to dx dash by dt dash is equal to d into x minus vt divided by dt is equal to, after calculation we get dx dt minus v, and dx dt is a rate of change of displacement in S frame. So, it is capital V minus small v. Now, try to understand that relation between v dash, v and minus small v. So, capital V is the velocity of the particle with respect to S frame, v dash is the velocity of the particle with respect to S dash frame, and small v is the velocity of moving frame. So, it is velocity transformation equation we discussed in our previous classes. Now, we are going to discuss about the acceleration transformation equation. If the particle moving with a velocity, then obviously it gets the acceleration. So, what is the acceleration transformation equation, how we derive transformation acceleration transformation equation, that topic now I am going to discuss. So, acceleration of the particle b small a according to S frame and a dash according to S dash frame, then a dash is equal to, a dash is the acceleration according to S dash frame. So, a dash means rate of change of velocity. Therefore, we write d by dt dash into dx dash by dt dash, dx dash dash by dt dash, it is the rate of change of displacement. So, it is symbolized by v dash, capital V dash. So, d dt into, now we get apply here the Galilean transformation equation. As you know that Galilean transformation equation is x dash is equal to x minus vt, y dash is equal to y, z dash equal z and t dash equal t. So, applying here Galilean transformation equation, we get d dt of dy dt into, in place of x dash we write x minus vt, and after simplification we write d dt into dx dt minus v. So, we get the d dt of dx dt. So, d square x dt square. So, finally, we get the d square x dt means it is the acceleration term and it is symbolized by small a. So, here you remember you observe that a dash is equal to a. So, a dash is the acceleration which is measured with respect to s dash prime and a is the acceleration of the particle with respect to s prime. So, we get that a dash is equal to a, that means acceleration is invariant, acceleration same for the Galilean transformation equation. It is seen that in classical physics acceleration invariant for the both observer, but when the velocity of moving particle is very high, then it has three component in three direction. We know that ux is equal to u dash x plus v divided by 1 plus v u dash x by c square. It is equation number 1. Then see, in previous classes we have discussed about the velocity component in three direction. One is x direction, one y direction and another is z direction. So, in three component we get the velocity direction. So, x direction velocity component symbolized by ux, and we derive in our earlier classes ux is equal to u dash x plus v divided by 1 plus v u dash x by c square. It is equation number 1. Then if we differentiate velocity with respect to time, then we get the acceleration term. So, taking differentials of equation 1, we get d of ux is equal to, applying derivative theorem, we get d u dash x into 1 plus v ux by c square minus u dash x plus v whole into v by c square d u dash x divided by 1 plus v u dash x by c square whole square. After simplification we get 1 minus v square by c square divided by 1 plus v u dash x c square whole square into d u dash x. It is given equation number 2. Also we know that t is equal to t dash plus v x dash by c square whole divided by root over 1 minus v square by c square. It is equation number 3. In Lorentz transformation equation we get the 4 equation, x dash is equal to x minus v t divided by root over 1 minus v square c square, y dash is equal to y, z dash equal z and t dash is equal to t minus Vx by c square whole divided by root over 1 minus v square by c square. It is Lorentz transformation equation. So, in Lorentz transformation equation, from x component we get the velocity and time component we get the equation number 3. So, from reverse equation, that is x is equal to in terms of x dash, t is equal to in terms of t dash. So, it is equation number 3. Taking differential of equation 3, we have dt is equal to dt dash plus v by c square dx dash whole divided by root over 1 minus v square by c square is equal to dt dash into 1 plus v u dash x divided by c square whole divided by root over 1 minus v square by c square, equation 4. Now, dividing equation 2 by 4, see, equation number 2 is ux and equation 4 is dt is equal to dt dash into 1 plus v u dash x by c square whole divided by root over 1 minus v square by c square. So, equation 2 by 4 we get u dot x, that is dux by dt is equal to, after calculation we get 1 minus v square by c square whole to the power 3 by 2 divided by 1 plus v u dash x by c square whole cube into u dot dash x. So, here you must remember that u dot x with respect to s prime and u dot dash x with respect to the s dash prime. So, one equation we get, one transformation equation of acceleration we get in x direction, it is equation number 5. Again we know that uy, it is velocity component in y direction, uy is equal to u dash y into root over 1 minus v square by c square whole divided by 1 plus v u dash x by c square. So, equation 9. and equation 10 gives uz is equal to u dash z into root over 1 minus phi square by c square whole divided by 1 plus phi u dash x by c square. It is velocity component in z direction. So, following the same procedure we obtain u dot y and u dot z. So, u dot y means acceleration component in y direction and u dot z it is acceleration component in z direction. U dot y, it is the two terms here, 1 minus phi square by c square divided by 1 plus phi u dash x by c square whole cube into u dot y dash minus phi by c square whole into 1 minus phi square by c square divided by 1 plus phi u dash x by c square whole cube u dash y into u dot x dash. So, one term you must remember that here u dot x dash term is involved in the direction of y direction. Similarly, in u dot z acceleration component in z direction, here also u dot x term included in the second term. So, it is 1 minus phi square by c square whole divided by 1 plus phi u dash x by c square whole cube u dot z dash minus phi by c square whole into 1 minus phi square by c square whole divided by 1 plus phi u dash x by c square whole cube u dash z into u dot x dash. So, it is equation number 7. It is observed that under Galilean transformation all laws of classical mechanics must be same and acceleration same for all observer in inertial frame of reference. So, under Galilean transformation it is seen that in we discussed already that all laws of mechanics are same. So, laws of mechanics based on Newton's first law, Newton's second law, Newton's third law, and these are the you know that especially we know that Newton's second law is F is equal to ma. So, it is invariant under the Galilean transformation. So, like this we can prove the first law and third law. So, same conditions here in under Galilean transformation, acceleration also same. Just we prove a dash is equal to a dash is equal to a. See this result, a dash is equal to a. So, under Galilean transformation acceleration must be same. Classical relativity based on two main pillars, these are classical mechanics and electromagnetism. So, in case of classical relativity there are two main parts, one is classical mechanics, another is electromagnetism. Classical mechanics are based on Newton's law and electromagnetism theory given by Maxwell's electromagnetism theory. Galilean transformation cannot prove the invariancy of Maxwell's law of electromagnetism and motion of a object which is moving with high speed. But Maxwell's theory deeply impressed Einstein because Maxwell theory gives the important result that light is an electromagnetic phenomenon, it has a constant speed. Maxwell gives the light theory is a electromagnetic phenomenon and it has velocity 3 into 10 to the power 8 meter per second. So, light is very important. So, Einstein deeply impressed by Maxwell's electromagnetic theory. So, he accept the Maxwell's law. So, he thought that another new transformation must be derived, so that Maxwell's electromagnetic theory also invariant for both frame S and S dash. Galilean transformation are approximation of Lorentz transformation for speeds very lower than the speed of light. Lorentz transformations are valid for any speed, whereas Galilean transformations are not. Galileo formulated the principle of relativity in order to show that one cannot determine whether the earth revolves about the sun or the sun revolves about the earth. The principle of relativity states that there is no physical way to differentiate between a body moving at a constant speed and an immobile body. So, Galileo formulated the transformation equation which is known as Galilean transformation equation, already we discussed, and Galilean proved that Newton's laws of mechanics, but he cannot prove that Maxwell's electromagnetic theory. Now, I am going to discuss about the basic concept of transformation equation of acceleration in special theory of relativity. In the field of physics, relativity improved the science of elementary particles and their fundamental interactions along with ushering in the nuclear age. With relativity, cosmology and astrophysics predicted extraordinary astronomical phenomena such as neutron stars, black holes and gravitational waves. In present universe, there is a question in everybody's mind that how relativity is used. So, in before starting the acceleration concept, in special theory of relativity, some important things here included in that how relativity actually work in the field of physics. So, relativity improved the science of elementary particles and the fundamental interaction, and also relativity mainly take part that cosmology and astrophysics. Also, it is the in present universe, it is relativity works in everywhere. So, how relativity used? The theory explained the behavior of object in space and time, and it can be used to predict everything from the existence of black holes to light bending due to gravity and the behavior of the planet Mercury in its orbit. In such a situation, acceleration plays an important role. So, when a object start to move with a velocity, then maybe when it gets the higher velocity, then maybe it has acceleration, and then how much acceleration here produced, and then how it is created or for what purpose acceleration produced. So, that topic also important to derive, so that we can say that what is the main equation or what is the main reason behind this. This is diagram for world line of accelerated reference frame. CT is the imaginary axis, and x this axis ax axis shows the space coordinate of a particle, and when we consider a accelerated frame of reference accelerated particle, then AC shows the AC is the bending line, and it shows the particle acceleration acceleration procedure. Then it is the actual diagram of it is known as Minkowski's diagram. So, two axes here, one is the space direction, another is the time direction. So, in accelerated frame, time direction time axis is the bending way, and first straight line first imaginary line axis is symbolized by CT, and it is CT dash. As noted above, acceleration is just time rate of change of velocity. We use the above result to determine how acceleration transform from one reference frame to another reference frame. Figure represent the world line of an accelerated reference frame with a time varying velocity ut relative to the unprimed inertial rest frame. Ut is the velocity with respect to time, and the frame, this diagram shows the accelerated frame, accelerated reference frame, and defining delta u is equal to ut minus u0. So, delta u means change in velocity, ut is the velocity in final position, and u0 velocity is a initial position. As the change in velocity of the accelerated frame relative to the unprimed frame between event A and C. So, two event consider here in this picture C, two event consider A and C. We can relate this to the change of velocity delta u dash of the accelerated frame relative to the inertial frame moving with the initial velocity u0. So, u0 initial velocity and ut the final velocity. Applying the equation for the relativistic addition of velocities, we find ut is equal to u0 plus delta u is equal to u0 plus delta u dash 1 plus initial velocity and change in velocity divided by c square. It is given by equation number A. We now note that the mean acceleration of the reference frame between events A and C in the race frame is just small a is equal to delta u by t, and a dash is equal to delta u dash by t dash. So, two mean acceleration we get a and a dash. From equation A we get delta u is equal to delta u dash into 1 minus u 0 square, u initial velocity square divided by c square, by 1 plus u into delta u dash by c square. C is the speed of light given by equation number B. The acceleration of the prime reference as it appears in the unprimed frame is small a, it is delta u by t, and it is given by equation number C. Since we are interested in the instantaneous rather than the average acceleration, we let t become small. This had three consequences. First, delta u and delta u dash become small, which mean that the term u and delta u dash divided by c square can be ignored. This means that a approximate to the delta u dash into 1 minus u square by c square whole divided by capital T. T is the time for the frame, accelerated frame. After some simple calculation, we find a relation between a and a dash. It is given by a is equal to a dash into 1 minus u square by c square whole divided by 3 by 2, which shows that the acceleration of a rapidly moving object as observed from the race frame is less than its acceleration relative to the inertial reference frame, in which the object is nearly stationary a dash by the factor 1 minus u square by c square whole to the power 3 by 2. So, this is the picture graph of a dash t divided by c. A is the acceleration, a dash acceleration with respect to the s dash frame, t time, and c light velocity, and u by c initial velocity divided by speed of light. So, in between the term we take a diagram. We get the following result. After calculation we get this result, a dash t is equal to u divided by 1 minus u square by c square whole to the power half, u by c is equal to a dash t by c whole divided by 1 plus a dash t by c whole square whole to the power half, and classically the velocity u would reach the speed of light when the term is equal to 1, a dash t by c is equal to 1. Now I am going to discuss some important question related to the acceleration, related to the velocity of a moving particle with respect to s frame and s dash frame. So, for that some important question I included in my lecture. These are: what are the fundamental forces in nature? So, there are 4 fundamental forces in nature. These are the gravity, electromagnetism, weak force, and the strong force. So, electromagnetism is associated with the velocity and the acceleration. Next, which theory gives the relationship between space and time? Special relativity or general theory of relativity? So, special theory of relativity explain the relationship between space and time. We discuss in our first unit. It is the 4-dimensional space time, and in the topic we discuss how space and time working together. Who develops the special theory of relativity? There are 4 options given: Michael Faraday, Galileo, Sir Isaac Newton, Albert Einstein. So, we know that Albert Einstein developed the special theory of relativity. How it is developed we discussed earlier classes. Now, another question here, true or false? The speed of light varies with respect to the person who measures and how fast the person measures it. The speed of light is constant irrespective of who measures it or how fast the person measures it. The relativity theorem states that space and time are relative and all motion must be relative to a frame of reference. Albert Einstein's theory of relativity includes special theory of relativity and general theory of relativity. Relativity theory states that there is no absolute reference frame. So, as you know that relativity theory deals with relative motion and relativity not accept the absolute motion, and relative motion is the motion which is the with respect to other frame of reference with respect to any other particles object, and absolute motion is independent. How does speed affect on time? That depends on how fast you are travelling. Thanks to Einstein, we know that the faster you go, the slower time passes. So, a very fast spaceship is a time machine to the future. 5 years on a ship travelling at 99% the speed of light, 2.5 years out and 2.5 years back correspond to roughly 36 years on earth. So, it is one example when we calculate the acceleration or in case of a gravity, then later we discuss in details. In special relativity, follow as in Newtonian mechanics by differentiation of velocity with respect to time. Because of Lorentz transformation and time dilation, the concept of time and distance become more complex, which also leads to more complex definitions of acceleration. Special relativity as the theory of flat Minkowski space-time remains valid in the presence of acceleration, because general relativity is only required when there is curvature of space-time caused by energy momentum tensor. However, since the amount of space-time curvature is not particularly high on Earth or its vicinity, SR remains valid for most practical purposes such as experiment in particle accelerators. So, here we just in this slide I show that difference between special relativity and general relativity. When velocity is non-uniform, then it produces acceleration, and then what situation will become, that topic difference mentioned here. One can derive transformation formulas for ordinary acceleration in 3 spatial dimensions as measured in an external inertial frame of reference, as well as for the special case of proper acceleration measured by a co-moving accelerometer. Another useful formalism is for acceleration, as its components can be connected in different inertial frames by a Lorentz transformation. Also, equations of motion can be formulated which connect acceleration and force. Equations for several forms of acceleration of bodies and their curved world lines follow from these formulas by integration. So, these are a brief description about the acceleration, how acceleration work with the moving particle. The Lorentz transformation was developed to make predictions confirmed by experimental measurements. Here why Lorentz transformation here mentioned that Lorentz transformation formula we use in the derivation of acceleration term. So, Lorentz transformation equation I mentioned earlier that it is x dash is equal to x minus v t divided by root over 1 minus v square by c square, y dash equal y, z dash equal z, and t dash is equal to t minus v x by c square divided by root over 1 minus v square by c square. So, it is Lorentz transformation. So, it is important to know that how Lorentz transformation is developed and for what purpose it is applied. So, Lorentz transformation was developed to make predictions confirmed by experimental measurements. The Lorentz transformation is relatable to all the events of physics. A Lorentz transformation is also known as a hyperbolic rotation for having a left fixed origin. The so-called Lorentz transformation 1904 was based on the fact that electromagnetic forces between surges are subject to slight alteration due to their motion, resulting in a minute contraction in the size of moving bodies. Also, it helps us to understand the concept of space and time, and it requires coordinates. To understand the space-time diagram and world lines, the speed of light is invariant in Lorentz transformation under inertial frame. So, there are so many importance of Lorentz transformation, and it helps how space and time working. So, it helps in our world line diagram, it helps derivation of acceleration. Lorentz invariance expresses the proposition that the laws of physics are the same for different observer. For example, an observer at rest on earth or one who is rotated through some angle or travelling at a constant speed relative to the observer at rest. So, these are now I am going to mention the consequences of Lorentz transformation. In my next class, I will discuss in details consequence of Lorentz transformation. So, consequences are relativity of simultaneity, length contraction, time dilation. In my next class, I will discuss in details. Thank you.